Welcome back to this specialization on high performance and embedded computer architecture. This lesson starts a new course called ILP, DLP and TLP. These acronyms stand for Instruction Level Parallelism, Data Level Parallelism and Thread Level Parallelism. The topic of this lesson is ILP Concepts and Challenges. First, a bit of motivation. This pipeline diagram shows a possible execution of a code snippet on a pipeline processor with multi-cycle operations. As indicated by the crossed boxes, there are many stall cycles. First, there are data hazard stalls caused by the fact that an instruction is dependent on a previous instruction that is still in the pipeline. And there are control hazard stalls caused by the fact that there is a delay between fetching a branch and executing it. In a previous lesson we saw that data hazard stalls can be eliminated by scheduling the instructions. But in this module we answer the question, how do we get rid of data hazard stalls when only the executable is available and we cannot reschedule the instructions in the code? As we will see, this leads to techniques called dynamic scheduling in hardware and out-of-order execution. The second question I will address in this module is, how do we eliminate or at least reduce control hazard stalls? As we will see, this is done using a technique called branch prediction. A second motivation for this module is multiple issue. The pipeline processes we have considered so far are single issue, meaning that the processes fetch, issue and execute a single instruction per cycle. The natural next step is to fetch, issue and execute multiple instructions per cycle. Modern high-performance processors all do so and are therefore called multiple issue processors. There are two multiple issue approaches. The first one is dynamic techniques. These techniques find and exploit instruction level parallelism largely in hardware. Desktop and server processors usually employ these techniques because in these markets backward compatibility is a must. Examples of such dynamic multiple issue processors are the Intel Core processors, the AMD Athlon, IBM Power 7, Power 8, etc. The second approach is static techniques. These techniques rely on software, in particular the compiler, to find operations that can be executed in parallel. Because the backward compatibility requirement is less stringent in the embedded market and embedded applications are usually recompiled for a new platform, static techniques are often employed in processors for the embedded market. But the Itanium processor from Intel was an exception. Examples of static multiple issue processors are the Trimedia processor from NXP, formerly Philips, and several digital signal processors from Texas Instruments. Let me now present the objectives for this module. Among other things, after this module you should be able to describe and apply the terms data and name dependencies, read after write hazard, write after write hazard and write after read hazard. Second, to describe and apply the algorithm of Tomasulo, which is the basic algorithm applied in all dynamically scheduled processors. Third, to describe how register renaming can be implemented dynamically at runtime in hardware. Fourth, to describe how branch prediction works and several advanced branch prediction schemes and the effect they have on the performance. Finally, you should be able to apply the techniques presented in this module. Concretely, that means that you should be able to indicate when instructions will be issued and executed in different types of processor cores. For example, a single issue dynamically scheduled core, a multiple issue dynamically scheduled core, and a multiple issue dynamically scheduled core with speculation. I already used the term ILP, but haven't given a precise definition yet. Instruction level parallelism is the property that computer instructions can be executed partially or completely in parallel. Pipelining, as we have seen before, is one form of ILP where the execution of different instructions is overlapped. Multiple issue, which is one of the topics I will discuss in this module, is another form of ILP where instructions are fetched, issued and executed fully in parallel. The natural first question is, where should we look for ILP? The simplest approach is to look for ILP within a basic block. A basic block is a code sequence with no branches in except at the entry, the first instruction in the basic block, and no branches out except at the exit, the last instruction of the basic block. To illustrate basic blocks, here's a small piece of code consisting of two statements, an if then else statement, and one other statement, y becomes y plus 1. This code consists of 4 basic blocks. The two statements before the if then else and the test x greater than y make up basic block 1. The if part constitute basic block 2, and basic block 3 corresponds to the else part, and basic block 4 corresponds to the statements after the if then else. Finding ILP within basic blocks is relatively simple to perform in hardware, but unfortunately the dynamic branch frequency, that is the number of branches executed divided by the total number of instructions executed, is typically 15 to 25%. That means that only 4 to 6 or 7 instructions are executed between two branches. Furthermore, instructions within a basic block often depend on each other, in which case they cannot be executed in parallel. Both facts imply that we must find and exploit instruction level parallelism across basic blocks. So where to look for ILP instead? Cores that exploit ILP, or simply ILP cores, usually find ILP in loops. Loop level parallelism denotes the property that the iterations of a loop are independent and can therefore be executed in parallel. Here's an example of a parallel loop, the addition of two arrays. Now, what ILP cores do is turn this loop level parallelism into instruction level parallelism, using techniques such as loop unrolling. However, loop unrolling is not applied statically in the source code, but dynamically in hardware using branch prediction. Dynamic ILP cores also speculatively execute the instructions predicted by the branch predictor. Speculatively means that the instructions are executed before knowing that they should be executed. Furthermore, dynamic ILP cores also apply register renaming in hardware in order to eliminate name dependencies. Dependencies that are present only because the same name is used, but there is no flow of data. In principle, with the emphasis on in principle, hardware software that tries to exploit ILP must preserve program order. Program order, sometimes also called thread order, is the order in which the instructions will be executed if they are executed sequentially, one at a time, as determined by the original program. Suppose, for example, that this is the program order, instructions I1 to I6. And let this be the data dependency graph, which has a node for every instruction, and there is an arrow from one instruction to another if the latter is data dependent on the former. The techniques I will describe in this module exploit ILP by preserving program order only when it affects the outcome of the program. For example, given the data dependency graph here on the right, these are both legal execution order, since an instruction is never executed before an instruction on which it depends. This execution order, however, is non-legal, since, for example, instruction 5 is executed before I3, but I5 depends on I3. Similarly, I6 is executed before I4, on which it depends. So this is not a legal execution order. This completes this video. Thank you for watching. In the next lesson, I will discuss data dependencies and exception behavior, the two program properties that an ILP core must preserve. Hope to see you back.